Hi, welcome to remote Gen Chem 2 lab. Coming to you live from my kitchen table. This is Dr. V, hi, and Dr. Weber's here.
Hi.
And we are having a really great time doing this for you guys. So, the first remote lab that y'all are going to do is going to take the place of the equilibrium constant of iron thiocyanate complex experiment. Basically, we're going to give you guys some hypothetical data, and you're going to have to work through all the math the same way that you would in the lab experiment. So in this video, what we're going to show you is how you're going to do that math in case there's any uncertainty about where the numbers are coming from or how to use it. So if you haven't already, you need to go and read that experiment, look through the data sheet, maybe even go ahead and mark it up like you're going to lab, and that'll make it a lot easier to follow along. Yay. So to start, we're going to give you an experimental procedure overview, just kind of summarizing it so that you can understand what we're doing here. Again, if you haven't yet, you need to go read the entire procedure, go through the background. It's very helpful, especially for your lecture right now. A lot of you guys were probably right in the middle of KEQ or about to start KEQ, so this would be very useful for you. So in the first part of the experiment, you would be given a Beer's law plot of standard solutions that contain a known amount of the iron thiocyanate +2 complex. Those standard solutions were made by having a massive excess of the iron 3+ cation and then a very small amount of the thiocyanate -1 anion. And the reason that it's done that way is that we know that if there's a huge excess of iron, that all of the thiocyanate has to be used up in the complex. Therefore, it's a known amount because we know how much thiocyanate was in the solution, and all of it is getting turned into the complex. The next part of the experiment has you measuring the absorbance of 3 equilibrium solutions to determine the concentration of the complex at equilibrium. So when we say equilibrium solutions, we mean that the concentrations of iron and thiocyanate are going to be much closer in order of magnitude. Whereas in the standard solutions, there is usually a couple hundred to 1,000-fold time more iron. In the equilibrium solutions, they're going to be much closer. Like you might have 5 millimolar iron and 3 millimolar of the thiocyanate. And therefore, they're actually at equilibrium, and there's no way of just knowing how much iron thiocyanate complex there is. After you do that, you complete the ice charts in order to determine the equilibrium concentrations of iron, thiocyanate, and the complex. So the iron thiocyanate complex concentration you are getting by taking your absorbance and plugging it in to your line of best fit from the Beer's law plot so that you can get the concentration. From there, you can back calculate how much iron and thiocyanate ions would still be present in solution at equilibrium, since they were not entirely used up to make the complex. Then, once you have your equilibrium concentrations of the iron, the thiocyanate, and the complex, you can calculate the KEQ of the formation of the complex. So for those of you who haven't gotten to KEQ in your classes yet, which is perfectly fine, we're going to discuss a little bit about equilibrium. So in this example for this experiment, we are using iron 3+ cation, thiocyanate minus anion, and together at a 1-to-1 ratio, they create the iron thiocyanate 2+ complex. So the idea here is that we are not going to use all of the iron and all of the thiocyanate and turn it all into iron thiocyanate complex. Instead, they're going to reach an equilibrium state where there's still going to be some iron 3+ ion, some thiocyanate minus ion in solution. Bless you, Dr. Walker. anyway, continuing on, there's going to be an equilibrium where all three species are still present. And to represent that equilibrium, we have a KEQ value. So all of you have already seen K values in your class. And so you know that this is a ratio of products over reactants. So you may have seen Kc or Kp. It's a very similar idea. We're going to use the concentration of the products at equilibrium and the concentration of our reactants at equilibrium to get our KEQ. So that's really the only thing that you have to think about here, is that we're talking about how much of these things are present at equilibrium. So for the iron thiocyanate reaction, our KEQ expression would be the concentration of iron thiocyanate complex over the concentration of iron times the concentration of thiocyanate. And again, these are all equilibrium values. So just like with K, the magnitude of KEQ means something. If KEQ is much greater than 1, which side of the reaction is being favored? Is it going to be the products or the reactants? We'll give you some thinking music. Probably enough thinking music. Okay, Dr. Weber, if KEQ is much greater than 1, what are we favoring?
The forward reaction is going to favor the products.
Right. So if KEQ is greater than 1, that means that the product side is favored. And we know that because KEQ is a ratio of products over reactants. So if the value is much greater than 1 or greater than 1 at all, that means that there is more products than reactants. Now, what if KEQ is less than 1?
The reverse reaction is going to be favored because the reactants are going to be more.
Right, so when KEQ is less than 1, the reactant side is favored because the denominator is going to be larger than the numerator. That's going to give us a value less than 1. So once you have all those concentrations worked out, you can plug them into your ICE chart. So your initial concentrations of the metal and ligand are actually going to be solved for by you using the amounts of stock solution that you're using to make your solutions. These are hypothetical solutions, obviously, because you're doing this from home, but you will use the M1V1 equals M2V2 dilution equation to solve for your initial concentrations of metal and ligand. Now the question is, how do I know how much metal ligand complex I'm starting with? Now the way that you think about this is that on the left-hand side here we have our reactants, on the right-hand side we have our product, and at the start of a reaction, how much product is actually present in the reaction? I'm going to give you a second to think about it. So before you've mixed together your metal and your ligand, how much metal ligand complex is present?
None.
None. Thank you, Dr. Weber. There is 0 metal ligand complex present. Now, let's say that you did your hypothetical math and you determined that there is 5 millimolar of the metal cation and 3 millimolar of the ligand anion. So those are our initial concentrations of what you're actually mixing together into a test tube. Now we have to figure out what our equilibrium values are, and this is the experimental portion. So go back to that first step, mentally. You had your Beer's law plot of those standards that tell us at this absorbance value, we know that there is this much of the complex present in solution. So if you take the absorbance of your metal-ligand complex, you can backtrack using the Beer's law plot line of best fit to figure out the concentration of the metal-ligand complex. Now the question is, where does that value go on the ice chart? So that value is going to go in the equilibrium slot. So whatever value you get from your Beer's law plot is going to go here in the metal-ligand complex. Now note that I said no quadratic formula needed. So we're not actually going to use X values. I'm going to give you some hypothetical numbers in a second, but I want you to think about how you're going to solve for all these other blanks. Because at this point, you have experimentally determined the actual value of X, an actual number and not a variable. So the rest of it becomes like a Sudoku essentially. So to calculate your change line, you have this value X, the metal-ligand complex therefore increased by positive X. What would the change line say for the metal and the ligand? Oh, that was fun. Okay. Man, great elevator music from YouTube. So the change line would say minus X because for every equivalent of the metal-ligand complex formed, you're using up one metal cation and one ligand anion. So you're using up equal amounts of each as what you formed of the metal-ligand complex. Therefore, for the equilibrium line, you're going to have 5 minus X and 3 minus X. Now in class, from here, you guys would then do all sorts of fun algebra. You'd have to use the quadratic formula to actually solve for X, or you would make some sort of assumption. But here we have an actual experimental value. So I'm going to erase a lot of the obnoxious marks that I've made here, and we're going to actually fill this in. Okay, so let's say that you actually measured the absorbance of one of your equilibrium solutions. And what you determined was that the concentration of the metal-ligand complex at equilibrium for this solution was 1.5 millimolar. That means that our change for the metal-ligand complex is equal to positive 1.5 millimolar. And then our change for the metal and the ligand concentrations is what, Dr. Weber?
Minus 1.5.
Thank you, Dr. Weber. So now this just becomes some straightforward subtraction. Now, something I want to point out about the way that this math was written out here is that we were not really paying a lot of attention to significant figures here. So let's pretend that we're using two significant figures. So, okay, using two significant figures, now we have that all the way across the board. The next thing that you'll notice on the ice charts provided to you in the experimental data sheet and then also on your fake Canvas data sheet is that there is a whole other line here for converting your equilibrium concentrations to molar. And that is because your KEQs are always expressed in terms of molarity and not millimolar. So in order to convert these to molar, we just need to divide by 1,000. So you've converted to molar concentrations. Now you can go and calculate your KEQ. So remembering that to calculate any type of K, capital K value, it's going to be products over reactants. Our KEQ is going to be equal to 0.0015 molar divided by 0.0035 molar times 0.0015 molar. And if you type that into your calculator, you should get 286. Now, one of the biggest mistakes that we see in this lab is actually in the usage of the calculator. So imagine you're typing this into your calculator. There's a couple different ways that we see people type it out. The first way is typing in 0.0015 divided by 0.0035 times 0.0015. Now, the issue with this is that if I type it in this way, my calculator is going to read it as divide and then multiply, and we'll end up with a very different answer. 0.000642, which is a very, very different number from 286. Another possibility is you can type in 0.0015 divided by 0.0035 times 0.0015 in parentheses. And when you do that, your calculator is going to read that it needs to do this multiplication first and then do the division. And that would give you the right answer. Another thing that you could do would be to, again, type out all your numbers with division signs between them. Because when a calculator sees a division sign, it tells it to put that number into the denominator. So this would also give you 286. Now, the last thing that we need to talk about is that when you're entering your answers in on Canvas, Canvas is very picky and it doesn't let us give you a range of numbers in the format that we've chosen for your lab experiment. So what you have to do is be really, really careful with your significant figures. So if we are using two significant figures for this problem, typing in 286 would not get me the right answer. Instead, I'd have to round to the nearest tens place, and that would give me 290. That would be a correct answer that Canvas will accept. Same with this wrong number here. We would want to cross out the 2 and use 0.00064, even though that's the wrong answer. So that's all the math you need to know, and we hope that this video helped you. And good luck with your remote labs, and good luck with the rest of your semester.